Hello everyone, here is Yuanhui and uh, now I will go over the homework 10 question 1. So in question 1 it's asking us from the lecture notes, collect the definition and simple property of the example of stochastic process. So let's go over that. The first one is Poisson process. So first we can see the number nt1 t2 of the point t in the interval t1 t2 of length t equal to t2 minus t1 is Poisson random variable with parameter lambda t. So the p n t1 t2 equals to k and equals to e power of minus lambda t and times lambda t power of k over k. Second, we can get in the interval t1 t2 and t2 t3 are non-overlap. Then the random variable u t1 t2 and t3 t4 are independent. And next is at a time movement t, there is no more than one Poisson point using the point t, we from the stochastic process xt equals to n0 t. So we need to list first order of the probability masses and mean and auto correlation and auto covariance. This four part we will list in the each of stochastic process in the each definition. So from above we can get the mean of the Poisson process is lambda t, which is linear function of t, and the autocorrelation function contains a term mean t1 t2 which come from the property of independence increment. And the second one is Poisson increment. So let's see. It's defined as yt equals to this function, where xt is Poisson process. First, and here is first order probability masses. Pyt equals to n over sigma, and mean expect value of yt equals to lambda, and autocorrelation is about the R22 and auto covariance is about the C1 C2. So from above we can get about the Poisson increment process. It's introduct to prepare us to define Poisson plus impulse process. And next one is for the Poisson impulse. From the Poisson impulse, we can see it's defined as zt equals to derivative of xt, where xt is a Poisson process. So it's defined as the time for each point. So probability masses, mean, autocorrelation, And so we can see the process ZT has zero mean and autocorrelation RT1T2 equals to lambda of sigma T1T2. And second is ZT minus lambda is a white noise, so which means there are some short noise. And the next one we will discuss is about the semi-random telegraph signal. So xt is defined based on the Poisson point again. The number of n_t1, t2 of point t1 in the interval t1, t2 of length equals to the t2 minus t1 is a Poisson random variable with parameter lambda. So let's see. For probability of n_t1, t2 is equals to k, is equals to e power of negative lambda t and times lambda t power of k over k, and so we can get first order probability methods, mean, autocorrelation, and autocovariance. So the mean is equal to expected value of xt equals to e power of minus 2 lambda t, and this from above we can see the probability of xt equal to 1 is not 1 over 2 and should be a little bit higher than 1 over 2. So when t1 and t2 are far away, x1 and x2 are least correlated. And for the next one, we're gonna see the semi-random telegraph signal. So from the above, we can see the random telegraph signal is yt equals to a times xt, and probability of a equals to 1 equals to probability of it's alpha. Probability of alpha equals to 1 equals to probability of alpha equals to negative 1, which is equals to 1 over 2, where xt is semi-random telegraph signal. So in first order probability methods, the probability of yt equals to 1 equals to probability yt equals negative 1 and equals to 1 over 1. The mean is expected value of yt equals to 0, and the autocorrelation it's RT1 T2 equals to e power of negative 2 times lambda and times the absolute value of T1 minus T2, and autocorrelation it's C22 equals to e power of negative 2 lambda the absolute value of T1 minus T2. So the probability of T1 equals to T equals negative 1 equals to 1 over 2. We can see that first the yt it might be SSS, and the expected value of yt is constant, and which means it's SSS. Next one is gonna be the random walk. So in the random walk, we can see. Let's make an example. Like we toss a fair coin n times, and k is the number of head in n toss, and so x n tau is equals to k times s and minus k times s, which is equals to the 2k minus n times s. So from that we can get the first order probability masses. The probability of xt equals to x n tau equals to r times x, which is equals to from n to n plus r over 2 times 1 over 2n. So in the condition is n times t, the t larger than n times t and smaller than n plus 1 times t. So the mean value is expect value of xt, which is equals to 0, and auto correlation is R22 equals to expect value of xt1, xt2 equals to xn tau and xn tau times xn tau, so which is equals to mean of n and m times s power of 2, and the auto covariance is C22 equals to same like above, and which is equals to mean n and m times s power of 2. From the above definition, we can see that the random walk is for the probability masses, we guess if n is equals n to infinity, n is infinity, we will have the Gaussian density, and then we can say for auto correlation function, mean n and m comes from property of independent increment. So that's random walk, and in the next is number 7, which is Werner process, and let's see. The Werner process, it's also called the Brownian motion, which is Wt equals to limit of xt and t to 0 s times power of 2 over t to alpha and to infinity, where xt is random walk. So for the Werner process, the first order density function is fWt 1 equals to 1 over square of 2 pi times alpha times t times e power of w power of 2 negative w over 2 over 2 alpha t. So the mean is expect value of Wt equals to 0, and autocorrelation is R22 equals to mean T22 times alpha. Same to autocorrelance. C22 equals to mean T22 alpha. So from that we can get it's Werner process. Its property is when W0 is equals to 0, so we can say WP is equal to 1, and when W has independence increment, which is WT plus N is independent of theta WS of X, which is as smaller and equal to T for mu large and equal to 0. And then W has a continuous path with probability WT is continuous in the T. So that it's the awesome part of question number 1. So I think for question number 1 that's it. Thank you for listening.